Okay, in this lecture, we're going to start in 1.3, and that's on building new, functions from given functions. So we're going to start with some elementary functions, ones that we learned in the last lecture, and we're going to learn how to build new functions from these in various ways. So let me share my screen. All right, so hopefully you can see this. So this is 1.3, new functions from old functions. And so as I said, there are a variety of ways to do this. You can start with the functions that we learned in the last lecture, and you can perform vertical, horizontal shifts, reflections, rotations, and then stretching and compressions in vertical and horizontal. And then on top of that, there's ways of making sense of adding two functions, multiplying functions, dividing functions. So you can take um, you can use the arithmetic on the real numbers and extend it or generalize it to functions. And then the last way we're going to look at is through the last way of building new functions from old functions is going to be done through composition. And this is going to be very important, especially later on when we um, learn about derivatives. We want to take derivatives of some very complicated functions. Well, you can actually simplify the process of differentiation a lot if you can view your function as a composition. So when you're able to view your function as a composition and you want to differentiate it, it can become a lot easier. It's just a matter of like when you have this composition, you have like a so-called inside function, inside piece, and a so-called outside function or outside piece. And the chain rule basically says that you can get the derivative of this very complicated function by differentiating each piece separately and then like combining this everything at the end in a certain way. Anyways, so that's looking ahead a bit. So the first type of transformations we're going to look at are translations. Um, so here's the table. I'm going to just go through this pretty briefly. So we're going to take C as a positive number. You can take it to the negative number and everything will work out perfectly fine. And we basically have the first two right here. These are your vertical transformations. And then these right here are your horizontal transformations. So these are going to be your horizontal. These are going to be your vertical transformations. And what basically distinguishes these two cases is that this number C, so we're transforming by this number, positive number C, it just depends upon where you add or subtract C. So you start with a function. So here's the setup. We have a function f of x, and we want to transform it in various ways. We want to perform some vertical or horizontal transformations. And so basically we're given the graph f. You can always take a simple model if you want. So if you want to keep in your mind this function, that's perfectly fine. This is the model I always use for understanding these transformations. And then you want to graph, say, f plus c. Well, now, so there's two cases, as I was saying. What distinguishes the vertical from the horizontal case is where you're adding or subtracting the c. So in this case, we're adding and subtracting the c on the outside of the function. Whereas in this case, we're adding and subtracting, in the horizontal case, we're adding and subtracting, or subtracting and adding before we evaluate the function. So in other words, here's like the order of operation for the vertical case. You take your x and you plug it into f of x, and then you add c. Whereas with the vertical, or so sorry, the horizontal, you take your x, you transform your x first, and then you evaluate that add function. And that will have a different effect depending on whether you add the c first, as in the horizontal transformation case, or you add the c after you evaluate your function. Now remember, so f of x is, so if I give you x, so actually just remember the graph of the function. The graph of the function This is what we're interested in, this set. We're plotting this set. It's x comma x, where x is in we'll just say domain of f, whatever it is, doesn't matter. Some domain. So this is obviously your x coordinate. Let me see. Oops. The first entry in this ordered pair, this is your x coordinate, and this f of x is your y coordinate. And this is how you plot the graph. You take an x value at some point on the x-axis, you plug it in your function, that'll give you some point on the y-axis, and then together they give you x, so you have x comma f of x together is a point in the plane. So f of x is always your y coordinate, equals the y coordinate. You plug in an x, you get a y coordinate out. And so in the vertical case, what this says, so let me clean this up a bit. What this says is that when you take f of x, so you plug in x to here, you get a y coordinate, and then you shift the y coordinate. So in other words, in order to graph, if you start with the graph of f of x, to get the graph of f of x plus c, you basically just shift all the y coordinates up by c units, and that's upwards. And that has the effect, and if you increase all the y coordinates, that means you're moving everything along the y-axis upwards, so you are shifting things vertically. That's why adding c or even subtracting c corresponds to a vertical shift. When you add c, you get a vertical shift upward. When you subtract c, you get a vertical shift downward. So when you subtract c, you're shrinking all the y coordinates. And remember, the y coordinate is basically like your height above. It's the height above the x-axis, or maybe below the x-axis in a sense. And so you're changing that height, and that's gonna, when you add or subtract c, you're changing that height. So it's going to correspond to a vertical. So that's why these are vertical transformations. For these ones, for the horizontal, they're honestly, to be fair, they are a little bit more confusing to conceptualize. So it takes a little bit of getting used to for these ones, for the horizontal ones. So in this case, you are changing. Actually, let's do what they say. They might. I'm not really reading the book. Maybe you're reading the book as I'm talking, and that's actually fine to do. Yeah. So here we go. So you have your f of x. Oops. Let's think about the horizontal case. I want to see what they say actually. So you have the f of x, and you want to plot this right here. This is, as I said, in C, some positive number. So this should be correspond to some horizontal transformation, but exactly how does that work out? Well, if you want the value of g at x, so you want to evaluate g of x, you have to shift your y. To get that, you need to evaluate f at x minus c. So you have to take whatever your x value is that you start with, and you have to shift it. You have to shift it. You have to move the x value around. So I guess the best way to figure out what's going on is to use a model for this one. The vertical case is kind of easier to figure out, I think, for most people. It's just you're changing the y coordinates. Whereas with the horizontal, you're changing the x coordinate. So before you even evaluate your function, you're shifting x values around. So let's just kind of get a model to see what's going on. So let's say g of x is equal to f of x minus 1. So that's going to be x minus 1 squared. So now a plot of x squared, remember, looks something like this. Now, this is when you subtract this 1, you're subtracting it from every single x. So like, in other words, I take this point right here, say this is 1. When you subtract 1, it moves over to this spot here to 0. So what that means is that this 0 point should shift over 1 unit. And that's exactly what you see. When you plug in g of x, g of 1, you get 1 minus 1 squared is equal to 0 squared. So in other words, this point right here, this x or y intercept shifts over to this spot right here, 1 unit. So in order to figure out the whole what happens to the whole shape of the graph, you really only need to fix one point on the graph. And the easiest point is to just take an x-intercept. So what that means is that this point right here, when you want to evaluate, say like this is x equals 1 right here. Let's not use x, but just say it's 1. Maybe zoom it maybe a bit too. So when you have 1 right here, when you plug in 1, in order to evaluate g of 1, remember you have to, and so as it says here, to get the value of g at x, so g at 1, and so we're taking in this case c to be 1 also. You have to take that value, you have to take x minus 1 or 1 minus 1 and evaluate it as f. But we know that f of 0 is 0. So this right here at x equals 1, g of x should have x-intercept here also. And now so in other words, what that means, as I said, is that this point right here that I've circled 100 times now, let me use a different color. This point right here, it shifts over 1 unit. That's the whole point of this discussion, is that single point shifts over 1 unit, but you're subtracting 1 from every value of x. So you could take an x over here and then just shift it over 1 unit and look at what happens. So everything has to shift over the same amount. And so this is, as I said, a rigid motion. So as long as you know where one point goes, you know where all of them go. So it's going to look like that. So when you subtract 1, you shift to the right. And that's what we have in this case right here. When you subtract c, a positive number, you shift to the right, and then it's going to be c units. When you add, you shift to the left. And again, if you want like another model, instead you can take f of x equal to x plus 1. And the reason why that's going to be a shift to the left is because when you plug in, so now let's say not f of x is that, but let's define a new g of x and say g of x is equal to x f of x plus 1. That's going to be x plus 1 squared. And now when you plug in g of negative 1, to evaluate that, you have to shift it, you have to add 1 to that input and then evaluate it at f. So in other words, you add 1 to the input. So you add 1 to the input and then evaluate it, which gives us 0. So g of negative 1 is f of 0, and we know f of 0 is 1. So we know that if you redefine g to be this right here, this point right here is going to shift over 1 unit, and so it's going to like open up like that. It's kind of messy, but hopefully you can see. Maybe use a different color. So now that when we evaluated at negative 1, and we found that when you evaluate g at negative 1, it's the same thing as evaluating f at 0. You have to add 1 to your input, and so it shifts over the whole thing like that. So yeah, always keep a model in your head. If you're unsure of, like as I said, like the vertical and the vertical case is like a little bit easier. It's like, oh, you're constantly adding you're uniformly adding c to all your y coordinates, so you're shifting up. You're uniformly subtracting c from all your y coordinates, so you're going to shift the graph down. So this one's a little bit easier to figure out. But the horizontal one, if you always keep a model in your head like this, and even this model will work for the vertical case. Like if you're not sure about the vertical case, keep this model in your head, keep the graph of x squared in your head, and just play around with different numbers. Like, like you could graph graph x squared plus 1, graph x squared minus 1, graph x minus 1 squared, and then x plus 1 squared. And just compare all of them, and you'll get a better sense of how this shifting works. So here's just a general example, I guess. So here's the graph we start with, and then this is various transformations. I guess this is stretching. We didn't get this stretching yet, but we will. So you can see, and we're just looking at figure one. This is translating, and it's a rigid motion. The shape of the graph doesn't change. Over here, you can see the shape of the graph is changing. Um, and we'll get to that in a moment. But over here, everything's rigid. So if you know where one point goes, you know where the rest of them have to go. So yeah, just give you a second to look at that. And now you can pause it, I guess. And now we want to look at stretching or reflecting or compressing. So we're gonna in this discussion, we're gonna fix some number c bigger than one, and we're given the graph of f of x, and we want to know what does this do. And we're always so there's this like dichotomy, and let me just point it out here. Actually, we have this dichotomy. We have that we want to transform by this factor of c. Okay, we have this factor of c in all cases right here. But depending on where you're multiplying, you're going to have a different result. So notice in the first two cases I kind of outlined right here, indicated, pointed out, we're multiplying by some factor c on the outside of the function. These are going to be your vertical transformations. And then you have this, so you have this dichotomy. You can either multiply on the inside of the function or the outside of the function. Outside the function gives you these vertical transformations. Inside gives you a horizontal transformation. And these are going to be stretching or shrinking, compressing. These last two are really just special cases, honestly. You don't need to memorize these. These are just going to be like reflections, though. You'll see that they're just special cases, though. Um, these are reflections. These last two. All right, so now if we multiply by c of x, so in other words, if we take x, evaluate f of x, and then we multiply by c, when we multiply this by this number c right here, on the outside, we're uniformly multiplying every y coordinate by c. And c is bigger than 1. So in other words, we're increasing the y coordinates. We're not increasing them in the same way that we are when we add c, because depending on what the value of x is, or f of x is, I should say, um that factor, it will just be by a factor of c, so it's increasing not in a uniform way. So we're increasing all the, so this should correspond to some vertical stretch. And when you multiply by 1 over c, so if c is bigger than 1, that implies that 1 over c is less than 1, and it's positive, of course. We're always taking everything to be positive. Then what you're doing is you're taking x, you're evaluating it at f of x, and then you're constantly multiplying by 1 over c, this relatively small number between um 0 and 1. So you're shrinking all the y coordinates. So it's gonna compress it vertically. All right, this is freezing for some reason. Let me stop sharing. I got a ton of windows open. I gotta close them. So I'm gonna stop. I'm gonna pause for a moment. All right, hopefully that works and my computer doesn't freeze anymore. So yeah, back to what I was saying. So you have in the second case right here, when you take x, you evaluate at f, and then you multiply by 1 over c, you're like uniformly shrinking all of the y coordinates, so it's going to compress things vertically. Now again, the horizontal case is a little trickier to figure out. Let me see. So for this, I guess it's good to have a model also. And so yeah, the vertical case, vertical, horizontal, or shrinking, vertical stretching, I should say more generally, um, is is sort of easy to figure out, just like with the vertical shifting. It's the horizontal case that could be a little tricky. And so for this, we have, well, let's see what they say. I don't know if they say anything in this paragraph. No, let's see. Oh yeah, so figure 3 illustrates these stretching transformations. So it's good to have okay, here's a good model to have, the cosine function. And they take c to be 2. You can take c to be Actually, no, you want to take c to be 2. So then you're going to compare the 1/2. So you're going to compare cosine x, 1/2 cosine 1/2 x, and then cosine 2x. Here, this right here, this figure, this part is just the vertical case. This is the vertical stretching. This case right here is the horizontal stretching, and that's really the case we're going to focus on right now. So basically what's happening here is, so first of all, we know that cosine x has period 2 pi. So that means cosine x, it implies that cosine x completes a cycle on the interval 0 to 2 pi. And that's really all we're, so this is 0 right here, and this is like right here is 2 pi. We're only graphing this over that. And then once you know what it looks like over, let's say 0 to 2 pi, or like most of the interval, you can figure out what it looks like on the whole real line. So let's look at first the cosine 2x. So when cosine x has a period of 2 pi, so cosine x completes a cycle on this interval. So now let's let t equal to 2x. So x is going to be some number between 0 and 2 pi. And if we multiply everything by 0 or 2, sorry, you get 2x is between 4 pi, but we just let t be equal to 2x, so we have 0, t is between 0 and 2 pi. So this implies that cosine of t, which we know is cosine of 2x, completes, let's say, 2 cycles on the interval 0 to 2 pi, right? So because when t goes from, so as t varies from 0, I'm sorry, when x varies from 0 to 2 pi, t varies from 0 to 4 pi. And so when you look at cosine of t has a period of 2 pi, and you're graphing it over interval of length 4 pi. So it's going to complete 2 cycles. It's going to go through its period twice or whatever. I think that's let's see. Yeah. The language gets a little funny because you're trying to figure out the best way to express things. But yeah, basically the idea is that when you look at cosine t, which is the same thing as cosine 2x, this is going to complete 2 cycles on 0 to 2 pi, because as x varies over the interval 0 to 2 pi, that is, as x is between 0 and 2 pi, t varies between 0 and 4 pi. So cosine t completes 2 cycles. And you can see that's the case in the graph. Look at this graph, the blue curve right here. It starts here. You can see it completes 2 cycles. It goes down and then it goes up. So there's 1 cycle, and then it goes down and then it goes up again. There's a second cycle. So over the interval 2 pi, it completes um two cycles. So what that means is that this corresponds to vertical horizontal shrinking. Like it's like you're compressing this cosine curve. So it goes through the period, it goes through its cycle faster in a sense. It repeats more often, in other words. Now when you do the other case, the 1/2, if cosine of 1/2, let's see. So again, cosine x has a period of 2 pi. So when x goes from 0 to 2 pi, that implies that 1/2 x goes between 0 and pi, or let's say this is t. Let's call t 1/2 x now. So this implies that cosine t, which is cosine 1/2 x, goes through, because if as x goes from 0 to 2 pi, t goes from 0 to pi, that's half of the period. So it goes through cosine t goes through half a cycle. Um, which is the same thing, cosine t is the same thing as cosine 1/2 x. And that's what you see here. It's not going the graph, this is in the green curve now, right here. It's stretched out. It takes longer to go through a cycle. And in fact, it only goes through half the cycle over the interval 0 to 2 pi. So that's what's going on when you multiply when you take your factor of c and you multiply the x first and then evaluate the function. So here's the vertical stretching, as I said. This is when you multiply the c or the 1 over c on the outside. It has you can see it has the effect of changing the amplitude. It's stretching it. But this right here, when you multiply by the 2 or the 1/2 first, and then you evaluate the function. So you do 2x, 1/2 x, and then evaluate the function at those points. It has the effect of changing the period of the function, changing the speed at which it repeats a cycle. Or in other words, it changes, it does a vertical, or sorry, it goes a horizontal stretch or contraction. All right, so hopefully that made some sense. Of course, it doesn't. We can always meet and try to go over this. Um, and if that doesn't make sense, honestly, like the best way to do mathematics is just a lot of people say it's the worst way to learn mathematics, but really it is the best way, is just to memorize these things. It is because once you can memorize these things, you've internalized them, and then your subconscious can like constantly think about this, so that when you're on the bus, when you're driving your car, when you're going to sleep at night, your mind is making these connections for you. And then that's literally how your eureka moments come about. These people, when these people who have so-called eureka moments, it's just their subconscious is finally making the connection for them. So you can't learn this stuff if you don't memorize it, in other words. So the first step in understanding is memorizing. So just if this description doesn't fully make sense, that's perfectly fine. It's kind of a complicated topic, but just memorize it for the time being. And then as you continue to memorize it and your subconscious operates on this information, it'll eventually make the connection for you. All right, so we have these examples. So we have this basic square root of x curve right here, and we want to, so this is going to be a shift. This is going to be a vertical shift downward. So this is down 2 units. This one right here, I won't write it out, but this is a horizontal shift to the right 2 units. This is going to be a reflection. So we have the 2x right here is going to be a vertical stretch. And then the negative x on the inside is also a reflection. But we're gonna have different reflections. So this reflection right here with the negatives on the outside, basically you what you do is you take x, you take the square root, you get a y coordinate, and that's going to be some point maybe here or here or here. But to get negative square root of x, you have to negate the y coordinate, so it's going to like flip down here. And that's exactly what you get over here. It's going to be reflected over the x-axis. So when you multiply by the negative on the outside, you reflect over the x-axis. When you multiply by the negative on the inside, you negate the x first and then take the square root. You have to that corresponds to this graph right here. It's going to be a reflection over the y-axis. So basically, like what you do is to evaluate this is you take some negative x, you negate it, so it flips over here. So like you have some negative x over here. You negate it, so this is like maybe -1. You negate it, you get 1. You evaluate it, you get square root of 1, and then that goes above the -1 point, because that's like the order in which you evaluate this function. So this is like -1, this is a 1. And then this is just a horizontal shift downward 2 units. Sorry, this is a vertical shift down 2 units. This is a horizontal shift to the right 2 units. This is vertical stretch. So, all right. Oh, and this is a technique you're going to want to know right here, completing the square, because you're going to sometimes be given a quadratic function, But it's not clear exactly, and you want to sketch it, but it's not clear exactly how you do that. But once you realize that this can be viewed as this right here can be viewed as some sort of transformation of your x squared function, it would be a lot easier to plot. You can see that when you do this, completing the square right here. So let's complete the square on the side. They don't go through it, but it's good to go through it. So you take half of the 6x, the half of the 6, and you add that in, so it's going to be so it's going to be 3 squared. But then you have to subtract that off, right? Plus 10. And then you can factor this bit right here as x plus 3 squared. And then this would be -9 plus 10 is plus 1. And that's why you get this right here. So it's a shift to the left 3 units and up 1 unit. So this point right here was 0, 0. And you basically, so you had 0, 0, and you shifted it over this way to the point -3, 1. And then all you need to know is where that one single point goes. So that's whatever. There's no point writing it. It's indicated right here, -3, 1. And as I said earlier, as long as you know where one point goes, say like the vertex, this is the vertex of the parabola, you know where the rest of the graph is going to go. So just keep track of one point, and it'll be clear how the rest of that moves. All right, so here's an example. So let's see, what did I do here? Yeah, so you do the 2x, so this is corresponds to a horizontal transformation, so it's a compression by a factor of 2. So this is our sine x, but then when you do sine 2x, so yeah, it's gonna repeat faster. So here's, I guess 2 pi, maybe. Yeah, I guess that's 2 pi right there. They don't indicate it, but the sine x is completes a cycle over the interval 0 to 2 pi. But when you multiply by this 2x, so x will go from 0 to 2 pi, but 2x goes from 0 to 4 pi. So it's gonna repeat twice, and you can see it repeats, and then sorry, it starts here and it goes up to here, and then that's one cycle, and then it goes through this here and it goes through another cycle. So in other words, you're changing the period of this graph. Yeah, it's because the period of this is, yeah, so because the period of this is a 2 pi, the period of y is sine 2x is 2 pi over 2 was pi. So it repeats over a smaller interval. Let's see, well, this one is not that bad. It's just the negative means you reflect over the x-axis and then you shift up 1 unit. So that's why you get this right here. All right, so now that's transformations, but now we want to look at combinations of functions. These ones are a little bit easier. There's not really like I mean, I think they give a picture. No, they don't actually. I was thinking the pre-calculus book. There's a picture like kind of illustrating how this works. So basically you have a function from A to R. There's no picture. So yeah, what I was trying to say is that there's no these transformations are a little easier to work with. These are new ways of building functions. There is the geometric way. I think, let me actually pull this up for a second. I don't know if it's super helpful. I don't think it was really helpful, but maybe it helps some people. This is the pre-calculus book. All right, before I show you what the picture in the pre-calculus book, let me just explain what's going on here. So you have these functions. F is a function from A to R, G is a function from B to R. So these real valued functions. So R has two operations on it, right? It has addition and multiplication. And then of course it has subtraction and division, but these are just like the same thing. Division is really the same thing as multiplication, and subtraction is basically the same thing as addition. So the point is though that your target R, your codomain R, has these binary operations on it of addition and multiplication, and so we can extend that to give us an arithmetic on functions. All right, so we have, if I give you a function So then f plus g is a new function. So let's say I want to define what it means to add two functions. So f plus g new function. And if it's a function, I had to specify the domain. It's from the domain is going to be the intersection of A and B because it has to be the common set. Um, because I'm going to evaluate points at both F and G. So I need to make sure that they're both defined at this. And so F plus G is a new function from A intersect B to R. But what's the rule? Well, the rule is this. I take a point X. And in order to specify a function, I have to tell you what it does to a given point. So take X, and it's just simply f of X plus G of X, what you would expect. And that's the formula they have over here. Now, here's an important thing about this formula. This addition right here is not the same as that. This is addition of functions. Okay. While this addition is addition of real, let's say real numbers. They're not the same. Now, what this shows is that this addition right here on the left-hand side is defined in terms of the addition on the right-hand side. And if you want to be technical, you could like put like a symbol on this to distinguish it. It's not necessary if as long as you can keep track of the difference in your head. You could say like this is plus hat. It's like a you put a caret on top of it. This is plus hat. Now, yeah, so this addition right here is not the same as this addition. They're different. Same thing with right here. There should be technically a dot right here for multiplication of these functions, and then there's dot multiplication for real numbers. The multiplication on this side right here is not the same as this. This right here on the left-hand side is multiplication of functions, which is defined in terms of multiplication of numbers because f of x and g of x are numbers, right? You plug in an x from A or an x from B, you get a real number out. And if you have real numbers, you can add and multiply them. So let's see, what do they say here? So yeah. Uh, okay, so here's an example, the domains. Um, oh yeah, so you have g f of x. I didn't finish subtraction and multiplication, but it's pretty straightforward what these mean. So again, like this division bar right here, this subtraction bar is not the same as this subtraction bar. This division bar is not the same as this division bar. They're different. One is defined in terms of the other though. So now you have this function square root of x, and then you have square root of 2 minus x. So the domain of f is just going to be 0 to infinity. And then the domain of g is this. So a intersect b is going to be 0 to infinity, intersect -2 to infinity. So it's clear that 0 is in both sets. Um, that's going to be like the leftmost boundary point. So it's going to start at 0 and um oh sorry, not -2, just +2. Wait, actually that's oh, I'm sorry. This is totally it's not -2 to infinity. It's negative infinity. Okay. It's really messed up. I messed up the domain. And it's right there. I don't know why I messed it up. It's negative infinity to 2. And as I said, 0 is in both sets, and it's like the leftmost boundary point, and then 2 is in both sets, A and B, so it's like the rightmost boundary point. So that's the domain, the intersection of these two. And then to the function, the addition of them is, so let me just write it over here if it's too cramped, is by definition, so f plus g at x is by definition f of x plus g of x. And f of x is just square root of x, and then g of x is square root of 2 minus x. So that's how you add functions. and subtract functions. And now for an example, there's another type of combination of functions that doesn't depend upon R having arithmetic, and that's a composition. This works for any type of functions, any type of functions. Um, so if I give you two functions f and g, you can find the composite function as f compose g. This is read as f composed with g. These symbols right there is read as f composed with g. It's called the composition of f with g, and it's defined as follows. So, basically, what you do is so if I wanted to find a function, again, it's a function as a set, that's two sets, domain and a codomain, with a rule. So, I'm not going to get into the details of the set, this codomain and the domain, but the rule, what is the rule? I have to tell you what it does to a given element. And basically what that is you take x, you feed it into the g of x. So you get this g of x here. That gives you some result, say a number. And now g of x is a number, so you plug that into f of x. So it's like you're like applying, in the case of addition of functions, you're applying both functions simultaneously and then adding them, like up here. But with composition, you're doing, there's like a layer, so you're doing one after the other. And here's a picture, I guess, if it helps you. You have like, remember, functions can be thought of as machines. So you plug x into this machine, you get a g of x, and that g of x can be fed through the machine f to get f of g of x, and that's by definition the composition. That these things are one and the same. So that's what this composition does to a given element x. All right, so we have an example here. I guess it's pretty straightforward. So so going from here to here, this is just by definition, right? This first step. Now you can do the composition and you can do it in different orders, right? Not always, but you can. Usually you'll be able to do it in different orders. Um, but don't be fooled by the form of this. Don't be fooled by this formula. You know, don't be fooled by the formula and the specific symbols in the specific order it uses them. So this tells you how to evaluate f composed with g, but you can very well just rearrange things to define g composed with f. So let's write that out over here. So g composed with f at x is, well, let's look at the original formula. Let's read it without symbols. Basically, you take the input. So I'm going to read this definition right here, symbol free. You take your input, you plug it into the closest function, and then you plug that result into the next function. So here's our input. The closest function is f. So I'm going to plug in x to f of x. And then that you plug into this outmost function, g of x. So that's how we get these two lines right here. These two first equations. These ones are just by definition. And then to get from here to here, we're using our specific functions. So g of x is x minus 3, so plug in x minus 3. And then to evaluate f of x minus 3, just wherever you see the x in the formula for f, replace it by x minus 3. So you get that. Now, for this second line right here, in the second equation, you have g of f of x. Well, f of x is x squared, so plug it in, so you get g of x squared. And now to evaluate g of x squared, just go to the formula for g of x, and wherever you see an x, replace it with the x squared. So you have x minus 3, replace the x with x squared. So you get x squared minus 3. And this is an important point. Note that these things, this operation is generally not commutative. So composition, let me write this over on the side. Composition is generally a non-commutative binary operation, unlike addition and multiplication. So this is a non-commutative binary operation in general. Up here, it's pretty clear, so it should be pretty clear that f plus g as functions, so maybe I'll just use the hat for a moment, is equal to g plus f hat, g plus hat f. And the same thing with multiplication. Actually, division will not be the same, and subtraction will not be. Yeah, division and subtraction are not commutative operations generally, but addition and multiplication are. So, and it might seem like this is like super obvious, like, but it is not. It's still something you have to prove. We know addition of numbers is and multiplication of numbers is commutative, but you still have to prove that function addition and function multiplication is commutative. It's like a one line. I'm not even gonna go through it. It's really trivial to prove, but there is something to prove still. All right. So now we want to look at, I guess, let's see. We'll just go through this one last example right here. And then maybe go through another section. So we have f of x is square root of x, and then g is square root of 2 minus x. We saw this one already. So we want to do, so let me put this to the side and I'll go through it over here. Um, oops. Because sometimes it's helpful to see things written out in real time. So let's see, we have f of x is equal to square root of x, and g of x is equal to 2 minus x. All right, so now we want to compute f composed g, g composed f composed f, and g composed g. So we'll do a first, and we want to find the domains of each function. So we want to compute f composed g at x. So this is going to be by definition f of g of x. Now g of x is square root of 2 minus x. So now we go to the formula for f of x and just replace x by square root of 2 minus x. So we get square root of 2 minus x. And this ends up being, when you take the square root of the square root, you get the fourth root. So it's fourth root of 2 minus x. And so the domain is going to be of this function. Let's say actually f composed g is going to be equal to sorry, negative infinity to negative sorry, not negative 2, just 2. All right, so that's f composed g. Now we want to do g composed f at x, and by definition it's just g of f of x, and then f of x, recall, is square root of x, so it's g of square root of x, and then g of x is square root of 2 minus x, so just replace the x by square root of x, so it's going to be square root of 2 minus square root of x. Now for this, we want, we need, so what's the domain here? This one's a little bit trickier, but it's not that bad. Domain. What's the domain of G composed F? Well, there are kind of actually two requirements that we need to simultaneously hold. So we have the square root of x, so from on the one hand, we need x bigger than 0, right? But then we have 2 minus square root of x inside of the square root, so we need that whole thing. Sorry, this would be greater than or equal to 0. So this one is done. That's pretty obvious. There's nothing to do to simplify this. So we just leave it that way. But now we want to solve for this one. So we add square root of x to both sides. So we have 2 is greater than square root of x. and then we can square both sides to get 4 is greater than x. So we want x greater than or equal to 0 and x less than or equal to 4. So that combining those, you can see that the domain is going to be 0 to 4. All right, so that's B. Let's do C now. So we want f composed f at x. By definition, that's f of x. And remember, f of x is x squared, so we get f of square root of x. And then again, f is square root of x, so you get square root of x, square root of x, which is going to be fourth root of x. And it's pretty clear that the only requirement is that x is going to be positive, so that this is like a requirement here, so that means the domain, let me just write it like this. Domain of f composed f is going to be 0 to infinity. And for the last one, we have part D. This is G composed G at x. So it's going to be G of x. And then G of x, remember, is square root of 2 minus x. And then G of x again is square root of 2 minus x. So replace the x by square root of 2 minus x. So it's be square root of 2 minus square root of 2 minus x. And again, we have two requirements. We want to find the domains. We have these two requirements. On the one hand, we have this square root of 2 minus x. So we need 2 minus x to be greater than or equal to 0. But then we have this square root on the outside. And so we need the thing in the inside of it to be greater than or equal to 0. So we get this. So this first inequality says that x has to be less than 2. So add x to both sides, so it's 2 is greater than or equal to x. For this one, let's see, so we're going to add the square root of 2 minus x to both sides. We get 2 is greater than or equal to the square root of 2 minus x. And now we square both sides. So we get 2 minus x. 4 is greater than or equal to 2 minus x. And now, let's see, I'm going to add x to both sides and then subtract 4 from both sides to get x is greater than -2. So combining these, we have x is less than or equal to 2, and x is greater than or equal to -2. So the domain of G composed G is going to be the interval from -2, going to be greater than -2, all the way up to 2, because you have to be less than 2. All right. So that's all we have for now. I think I don't know if this will be a whole video. Maybe I'll add some more. I'm not sure, but I'm going to pause for a moment.